All right, well, this question is determine the percentage of the calcium carbonate in a shell of hen's egg a student dissolved in 1.572 grams of dried eggshell and 50 centimeters cubed of 1 mole per decimeter cubed hydrochloric acid. After all the shell had completely reacted to the acid, okay, that's a good thing to presume, the resulting solution was diluted to 250 cubic centimeters in a volumetric flask. 25 centimeters cubed samples of this diluted solution were titrated with 0.1 mole per decimeter of sodium hydroxide solution using the, I can never pronounce this, phenolphthalein as a indicator. The average volume of the sodium hydroxide in water solution required to reach the end point was 19.4 cubic centimeters. Determine the concentration of the diluted hydrochloric acid solution. All right. So, the trick to knowing this is that we're going to use back titration. Okay. We're going to use back titration, and we are going to add excess hydrochloric acid, so there's going to be more hydrochloric acid than we need, but we're just going to do that so that we know that it's all done, and whatever the hydrochloric acid that's left over, we can then work out how dilute the original amount was. It's completely, we're going to add that excess to completely dissolve the calcium carbonate, and then take the and then we titrate the remaining hydrochloric acid with the sodium hydroxide to find out how much hydrochloric acid didn't react. After that, we can work out the concentration of the hydrochloric acid. So if we know how much didn't, we know how much did, so we can kind of work it out that way. We can be kind of tricky. So there's a few things to presume here. We're presuming that it's done in standard conditions, and we're presuming that everything, all the dissolution goes completely, everything is used up when we put the acid in. There's no error, there's nothing like that. Okay, so it's a sort of hypothetical experiment really. First thing we need to do is we need to take an inventory of what we've got. An inventory of what we've got and what we want. Right? So let's have a look at what we've got. So we're told that we have a mass of dried, what are the eggshells? Eggshells, I presume they're chicken's eggs, and that is 1.5772 grams, and that's that right up there. Next thing we're told, we're going to presume that this contains the that, which is a pretty safe assumption to make really. Then we're told the volume of the mole of the DC 1 mole of the DC 1 mole decimeter -3 hydrochloric acid, and that is, we're told that's 50 centimeters cubed, but we need to really translate that into decimeters, which is going to be 0.05 decimeters cubed. 0.05 liters really. So the final diluted volume, we're told, is 250 centimeters cubed, which we would put into decimeter form, and that's going to be equal to by thousands, 0.25 decimeter cubed. And then we have the sample volume really of the titration. And that's going to be 25.00 centimeters, and we need to convert that really to 0.025 decimeters cubed. Okay, and then there's another one that they give us. They give us a lot, actually, don't they? So the average volume of the sodium hydroxide required, and that's going to be equal to 19.40 centimeters cubed. That's what they give us up here. And I'm going to need to translate that, I think, in the future to SI units. So it's going to be 0.0194 decimeter cubed. So a bit of a mess there, but that's what we've got. So that's what we're going to be working with. Work out the chemical reactions. Well, dissolution. Work out the chemical reactions. So the chemical reactions, we've got the calcium carbonate, which is going to be a solid plus 2Cl which is going to be in water, and that's going to be calcium dichloride, also in water, plus H2O, which is water, plus CO2 gas. And we can even say this is excess okay, and then the titration itself, that's going to be hydrochloric acid in the water plus the sodium hydroxide. So this is the thing we're going to do last, and that's going to go to sodium chloride, table salt, plus good old H2O, and that's going to be in its liquid form. All right, the next thing we want to do is we need to calculate the moles of sodium hydroxide. So now this is really not really chemistry. This is now a mathematical problem. So our third step now is we're going to calculate the moles of the NaOH used in this titration. Okay, so the volume of the sodium hydroxide is given to us as 0.01940 decimeters. I think actually I might have worked that out beforehand. And the concentration of the NaOH is going to be 0.100 moles per decimeter cubed. So the amount of the sodium hydroxide is going to be the concentration of the sodium hydroxide, should be square brackets there, times the volume of that sodium hydroxide. And that's going to be what, 0.100 times 0.01940, which is going to be 0.00194 moles, which is 1.94 times 10 to the power of 3 moles. Tiny, but it's still going to be the same amount of moles. Okay, next step, we calculate the moles of excess. So this is step 4. We're going to calculate the moles of excess hydrochloric acid, because we know how much hydrochloric acid is left over after we've used it to get rid of the calcium carbonate. Then we can work backwards. That's in the titration. Okay. And we know that 1 mole of hydrochloric acid is the same amount as 1 mole of the sodium hydroxide, because they reacted 1 to 1. So if there were more moles of hydrochloric acid, then all of them would be used up, but there would be no moles of sodium hydroxide left over, because it's always chemical reactions. We always calculate them mole to mole. It's not volume to volume. Okay. Now what do you do? So they told us, therefore, that the excess hydrochloric acid in 25 centimeter cube sample is equal to 0.001940, because it's the same as the mole of sodium hydroxide that we worked out right there. Same as that. Okay, so the amount of the moles of sodium hydroxide that we used in this back-titration must be the same number of moles that we used of sodium hydroxide, and anything left over is the excess in hydrochloric acid. Okay. What am I doing? I give everything right there. It's right there. Okay. Fifth step. We're going to calculate the moles of excess hydrochloric acid in the solution. And solution is 250 centimeters cubed. So 25 centimeters cubed. Just going to test that. I'm just going to. So I just wanted to check something, because the 250 came from nowhere, but the 250 comes from up here. That bit there. So I sort of double checked that. Okay, so it says 25.00 centimeters cubed as 0.001940. And I'm going to leave it like that, non-scientific notation. Moles of excess hydrochloric acid, and 27.00 centimeters cubed as, and this is the formula that we're going to use. So it's the molar amount, 0.00194 moles times 250 of the original, divided by that 25 centimeters cubed, and we get 0.01940 moles of excess hydrochloric acid, which shouldn't really surprise you, because it's what we got here. But we've sort of worked it out in the old amount. So now what do we do? Now we're almost there. We are almost there. Now, in step 6, we can calculate the moles of CHL originally used. Okay. So the volume of the hydrochloric acid, as I can say the original, is equal to 0.05 decimeters cubed. And the concentration of that is going to be equal to 1.0 moles per decimeter. So the total moles is of HCl, hydrochloric acid, originally used. That was sort of saturated, that was sort of diluted into the solution, is going to be equal to that amount there. That's how much we've got, minus 0.0194 equals 0.0306 moles. Nearly there. Nearly there. Okay, next step is we want to actually calculate the concentration of the diluted hydrochloric acid. And we're going to let's take a just tick my notes. So we want to, what do we want to do? Okay, so we're going to say the excess HCl which we worked out as 0.01940 moles, is now dissolved into the 250 centimeter cubed solution from the original question. This one here. This bit right here. So we know that the concentration of the dilute hydrochloric acid is going to be equal to the number of moles. So it's going to be the N number of moles divided by the volume. All right, so that's going to be equal to 0.01940 divided by this number here, which is 0.23. That number there, 0.250. and we get a final answer, hooray, of 0.0776 moles per decimeter cubed. Oh, that's a lot of work for 3 marks. It really is. But that's what it is. Okay, any questions, let me know. Send a message, send an email, and I'll see if I can maybe even do a better version of this. But I've just kind of like gone through it. It's pretty gory.